Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in chapter 1, part of this playlist that we're calling Probability. And let's jump to today's topic, which is independent events. Now, two events A and B are independent if they have no effect of occurrence or non-occurrence on each other. Thus, the probability of A given B is really just the probability of A. Now we do have to assume that the probability of event B is greater than 0. So knowing B doesn't affect the probability of A. And it's the same, and it's the other way too. The probability of B given A is just really the probability of B. And so this leads to the given theorem here. So the events A and B are independent if and only if, and sometimes you just shorthand it IFF. It's the probability of A and B, and of course you can write it just probability AB, which implies intersection, is equal to the product of the marginal probabilities, probability A times probability B. And a quick proof of this is from the multiplication rule of probability. We have the probability of A intersect B is equal to this multiplication rule of conditional probability. But the probability A given B is just, right? Since A and B are independent, the probability A given B is just probability A. So you put that in there and the result follows. Now let's do an example. A balanced die is rolled. Let the event A equal the even numbers observed, and the event B be that the numbers 1, 2, 3, 4 is observed. Show that the events A and B are independent. Well, the probability of A is 1/2, right? Even numbers observed. The probability of B is 4/6, which is 2/3. And the probability of their intersection is 2/6, right? There's two even numbers out of the 6, so it's 1/3. And since the probability of A intersect B is equal to the product, they're independent. Now, two events A and B are independent. This is a theorem. Then the events A and B complement are also independent. So A and the non-occurrence of event B are independent. And here's a quick proof. Now the A can be separated into the union of disjoint sets A intersect B and A intersect B complement. So that means the probability of their intersection is the sum of their probabilities. So that's how we go from here to here. So probability A is equal to these two probabilities. But if we subtract the probability of the A intersect B to the other side, then we get this. The probability A intersect B complement is equal to the probability A times the probability A B. But since A and B are independent, this is the product of the marginals. So the probability A and then minus their product. But we can left factor out the probability of A, and we get probability A times 1 minus probability of B. But 1 minus probability of B is B complement. So the intersection does equal the product of the marginals. So they are independent. Now this also expands to several events. So the K events, A1, A2 to AK, are independent if every subset of these possible K events, and so we don't know what a subset is, so we need new subscripts. So I1 to IJ, and J of these events can be 2, 3, up to K. So if J is 2, then there's only 2 sets here. That's the subset of the original K. There's only 2 of them. But when J is 3, then there's 3 subsets here. And so, but whatever, however many sets you pick in that subset, the probability of their intersection has to equal the product of the marginals. Then they're independent. Now, what's an interesting example here is that this is an example that every set is pairwise independent, but all the sets are not independent. And so an experiment has a sample space S with 4 outcomes, S1, S2, S3, S4, each with probability 1/4, right? So you add them up, that equals 1. So the probability of S is 1. Define three events A, B, and C as follow. A is S1 and S2, B is S1 and S3, and C is S1 and S4. So note that the intersection of these events, so A intersect B is S1, right? Though S1 is the only one common. Intersection A and A and C intersect B and C, and actually the three-way intersection ABC are all S1. So if we look at the probability of A, that's 2 out of 4, which is 1/2. Probably B, probably C are all 1/2. But the probability of these intersections is 1/4, right? But if we look at the product of probably A and probably B, that's 1/2 times 1/2, which is 1/4. So all these two-way or pairwise comparisons are independent. But the three-way, the product of probably A, probably B, probably C is 1/8. That does not equal the probability of the three-way intersection. So these events are not independent, but they are pairwise independent. And there's actually a lot of theorems that reduce this restriction of independence to they're just pairwise independence. Okay, example, rolling 2 die. So 2 die are rolled repeatedly and the sum T is observed for each roll. We want to find the probability of rolling a 7 before rolling an 8. And I have two different solutions. And if you know the game of craps, which is a dice game, this is exactly the probabilities that you'll need to calculate. So we want to estimate the probability of rolling a 7 before rolling an 8. You just keep rolling and keep rolling until one of those occur. So let's let AJ be the sum is 7 on roll J, and let B sub J be the sum is not 7 or 8 on roll J. So the probability of rolling a 7 before an 8 is this. We could roll a 7 on roll 1, so probably A1. On roll 2, we could roll a 7, but that means we should not roll a 7 or 8 on roll 1. So that's the probability of B1 and A2. But we could also win on roll 3. So that's the probability that we don't roll a 7 or an 8 on roll 1. We don't roll a 7 or 8 on roll 2. And we roll a 7 on the third roll. And this goes on forever. So we start looking at these calculations. The probability that we roll a 7 on roll 1 is 6/36. Here, so each time we pick up the die and roll, it's actually independent of the previous roll. So this is the product. Probably that we don't roll a 7 or 8 is 25/36. Probably we roll a 7 is 6/36. And then this goes on forever. So if we left factor out 6/36, we get this right here. But this is, each of these probabilities are less than 1. So this is a geometric series which converges to this 1/1 minus 25/36. Well, then you can calculate this to be 6/11. And so this is the probability we roll a 7 before we roll an 8. Now that's solution 1. Now solution 2 is if we let A roll a 7 and the event B roll a 7 or an 8, the probability that we roll a 7 before an 8 is actually the probability of event A given event B. So this says the probability that we've stopped. What's the probability that we roll a 7? And it's the same. So this is conditional probability. So the probability of A intersect B over the probability of B. But A intersect B, so we roll a 7, intersect, roll a 7 or 8 is actually the same as just the probability of A, which is 6/36. Probably a B is 11/36. This is 6/11. It's the same. And this second way of solving it, remember it in this next example. And it's our last example. And it's the game of craps, which I was talking about earlier. And here's a brief explanation of how to play. The first roll of 2 die, let t equal the sum of the die. We instantly win if t is a 7 or an 11. We lose if t is a 2, 3, or 12. Now, if t is not one of these numbers, we pick up the die and roll again. But on the second roll of 2 dice, this is assuming we didn't win or lose on roll 1, we continue to roll until t or 7 is observed. Remember, t is what we rolled on the first roll. So it's a number, not one of these 5. We win if t is observed before 7, and we lose if a 7 is observed before t. And so we want to find the probability p that we win. And here's the answer. Okay. First of all, let's develop notation. So pi sub 0 means we win on roll 1. Then let pi sub j equal we win by rolling t twice. So for example, on roll 1 we roll a 4, and then we need to find the probability that we roll a 4 before a 7. And that's what pi sub j is. And j can take on 4, 5, 6, 8, 9, and 10, because those are the numbers that you don't win or lose on roll 1. So the probability that we win is actually the sum of these probabilities, pi 0, pi 4, pi 5, 6, 7, 8, 9, 10. So let's start calculating. So pi 0, the probability we win on roll 1, is the probability t equals 7, or, which means union, t equals 11. 6 ways to roll a 7, 2 ways to roll an 11, so it's probability 2 over 9. Now, the probability, or pi 4, the probability that we roll a 4 twice and win, is, well, it's the probability we roll a 4 on roll 1, and then it's the probability we roll a 4 given that we've stopped. We've either rolled a 4 or a 7. And I'm going to point you back to the first example on how to calculate that. But it's 36 over 6. That's probably the number of ways you can roll a 4 on roll 1. And then it's 3 over 9 for this probability. Probably we roll a 4, given that we've rolled a 4 or 7. And that is 1 over 36. Now, since the dice are symmetric, actually the probability that we roll a 10 twice, pi 10, is actually the same as pi over 4. So it's probably that we roll a 10 on the first roll times the probability that we roll a 10, given that we've rolled a 10 or a 7 on, we've stopped. It's actually the same probabilities, 136. So the pi 5 and pi 9 are exactly the same. So it's 4 over 36 times 4 over 10, which is 2 over 45. Pi 6 equal to pi 8, because the dice are symmetric. That probability is 25 over 396. So the probability of winning craps is the sum of those probabilities, which is 0.493, which is actually pretty close to 50%. And craps is, like, if you ever go to a casino, it's actually one of the games that is most favorable for the player, because it's almost a 50-50 chance of winning. It's a slight advantage to the casino. Okay, we're at 13 minutes. I'm going to call this video quits. I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.